In this video, we're going to talk about the ideal gas equation, PV equals nRT. We're going to go through the conversions you need to use this equation, and we're going to go through lots of examples to make sure that you know all of the exam-style questions that you will be doing in the exams. So the ideal gas equation is PV equals nRT. Do not worry about all the information about this equation that you need to know for physics. In chemistry, all you need to do is be able to use this equation. So to use this equation, we need to know all of the different units. So let's go through what each part of it means. First of all, pressure. So your P that you have here is pressure, and that is in pascals. The next one is volume. And so the volume of the gas will be in meters cubed. The number of moles of the gas that you're talking about is going to be there for N. And then the gas constant, which you can find on the data sheet, which is 8.314, okay, is R. And then your temperature is T. The temperature is in Kelvin. So we can use this equation to find out the pressure, find out the volume, or find out the temperature of, or the number of moles, sorry, of a gas. So if you come across a question that includes any mixture of these different values, it should tell you it's a PV equals nRT question. But let's look at those different conversions that we might need. So our exam tip here is recognize the units you need, which are on here. Okay, and then recognize what are the conversions. So we need to know units, and we need to know those conversions. So we'll go over those conversions next. So here we have pressure in pascals, and we'll normally be given pressure not in pascals, but in kilopascals. So how do we change the kilopascals to pascals? We do that by timesing by 1,000. This kilo here is with times, it means that you have to times by 1,000 to get back to pascals. Obviously the other way around would be to divide, but we don't generally have to do that in using this equation. So the volume is normally in meters cubed in the equation, and it gives you meters cubed if it gives you a volume. So you have to change sometimes centimeters cubed to decimeters cubed to meters cubed, and you do that by dividing by 1,000 and then dividing by 1,000 again. So if, for example, you're given this, you're given centimeters cubed, and then the centimeters cubed has to be converted into the meters cubed, okay, that means that you divide by 1,000, divide by 1,000 again. Now you can also divide by 1,000,000 instead. And the last option is if you're good at maths and you're good at using your calculator, you can use something called the times 10 to the x button. If you press times 10 to the x and then put in -6, it will divide by 1,000,000. If you want to go the other way, for example, we want to turn meters cubed into dm cubed or centimeters cubed, we'd have to divide times by 1,000 and then times by 1,000 again, or times by 1,000,000. Or the third option again is use the times 10 to the x button, and this time put times 10 to the x 6. So if you're dividing, it's -6. If you're timesing, is 6. Again, that will give you the right number. We'll show you that throughout the video. The next thing is number of moles, which is mole. And then we go to the gas constant, which is 8.314 joules per Kelvin per mole. And the gas constant, remember, is on the data sheet. And then temperature. Now, 0 degrees Celsius is 273 Kelvin. So 0 degrees Kelvin is 273 degrees below 0 degrees Celsius. So if you want to change 0 degrees Celsius to Kelvin, you would add the 273 back on. So simple conversion, degrees Celsius to Kelvin, add 273. And these three conversions, okay, will be the most common conversions that you use in this question. So let's make sure that you know them. So times by 1,000 for pascals, divide by 1,000,000 to do centimeters cubed to meters cubed, and plus 273. Now let's go through the first question in our series. Now the first question is just really going to be talking about putting the values into PV equals nRT and doing the unit conversions. First of all, we need to recognise what we have in the question. We have a number of moles, and we know it's completely decomposed. That means it's 100% yield. It's gone all the way to make the products. And then we're calculating the volume of the phosphine gas. The phosphine gas is the pH3, so it's a gas, and we're calculating the volume of that gas with the ideal gas equation. We need to know how much of the gas is formed in centimetres cubed. We're given kilopascals, which means we'll need to convert, and degrees Celsius, which means we'll need to convert. Now the important thing is though, if I go back to the centimetres cubed, it's asking me 4 centimetres cubed, okay? And I'm given in the question when I calculate this volume, it will come out in metres cubed. So let's change this conversion to change metres cubed to centimetres cubed because that's what we want in the question. And all we've done is times by 1,000, go the opposite way. So if I want to turn metres cubed to decimeters cubed, times by 1,000, then times by 1,000 again, or, as I said, times by 1,000,000. So if we look at this question and we give ourselves some space to go through the answer, so we're going to move it to the side, and we've got our equation up here. So the most important thing to start off with is the question wants volume. We've highlighted all the bits that we need in this equation from the moles, the fact we're calculating volume, the fact we want centimetres cubed, we've got to convert kilopascals and degrees Celsius. So we know we've got to create centimetres cubed and we know we've got to create volume. So we rearrange this equation to equals volume. What we do is bring the pressure down, divide by the pressure. Now this is a really important exam tip. Exam tip is this gets you a mark. So even if you don't know how to do the rest of the PV equals nRT question, convert the equation into whatever you need to calculate. So in this case, we're calculating volume, so rearrange it. That gets you a mark. So now let's actually go through the question itself. We have 0.00560 moles of H3PO3. So this is this here. And we are making pH3, which is what we want to calculate, the volume of this, and phosphoric acid. Now the important thing here, when you look at it, is the ratio here is 4 and it is 1. Okay, so 4 to 1. So the ratio of the H3PO3 and the pH3 is 4 to 1. So I know the number of moles of H3PO3 I've got, okay, and I know that that number of moles I'd have to divide by 4 to get the moles of pH3. So we'll put that into our equation when we do it, okay? So let's start off with our volume. So we have our volume here, and then we're going to start off with our number of moles. I'm going to put this in a bracket. Okay, and I'm going to put in the number of moles. And there's our number of moles of this H3PO3, 0.00560. We need to convert the number of moles here into the number of moles of pH3 because that's what we're calculating. That's a 4 to 1 ratio. So therefore I divide that by 4. Okay, so that is our number of moles. So our number of moles is then, according to our PV equals nRT, we're going to times that by the gas constant. Okay, so that's 8.314. We then times it by the temperature, and now the temperature here is 100 degrees Celsius. 100 degrees Celsius plus 273 is going to be 373. So we've got all of our information here, and just going back through that again, here's our number of moles, which we use the equation and the balancing in there to find out the exact number of moles of the pH3 here. That's from the data sheet, 8.314, which is R, and then here is our converted temperature now in Kelvin and not in degrees C. I would put all the units on, but it fills up the board a little bit too much, so therefore I've left the units off for now. We then divide that all, and we divide it by P. Now P is 101 kilopascals, so we need to times that by 1,000. That'll be 101, okay, and that is in pascals. So if that is in pascals, and we put that through our calculator, we'll find out that V equals, okay, so V is going to be equal, and we will get 4.298, and it is 4.298 times 10 to the minus 5. Okay, and that's 4.298 times 10 to the minus 5. Okay, but that is in meters cubed. Now the question itself did not ask for it for meters cubed, it asked for it in centimeters cubed. So what I have to do from that point, and remember I said use the times 10 to the x button. So if I'm using the times 10 to the x button, I can times this whole thing if I want to times it by, for example, I want to times it by 1,000,000. Remember I want to go from meters cubed to centimeters cubed, so I want to times it by 1,000,000. I can put this in my calculator, put in times 10 to the x, and that times 10 to the x will then turn into timesing it by 1,000,000. Remember that number is 6. So V in the end is going to be 40, okay, 2.98. But because we normally have this in 3 significant figures, okay, I'm going to do it in 3 significant figures. So to 3 sig fig, okay, that is going to be 43.0 centimeters cubed. Okay, so we have a whole equation where we've taken PV equals nRT, we've rearranged it to equal V, volume. We then use the balancing equation to turn it into the right number of moles, the gas constant, the temperature conversion, the pressure conversion, and then we created it in meters, but the question wants it in centimeters cubed, so we times that by 1,000,000, we get 42.98, but to 3 significant figures, we're going to turn that into 43, and that means you end up with a final answer of 43 centimeters cubed. Our next style of PV equals nRT question is where you have to determine the molar mass and then the molecular formula. You need to use 2 equations, PV equals nRT, and then you have to use moles equals mass over mR. It's useful here to think of moles with the same label, so N and N, because then you can link the 2 together and say, well, that N is the same as that N. So if I work out the number of moles here, I will know the number of moles in this equation. And for example, if I'm given the mass, I can work out the molecular mass, okay, or the molar mass. And basically that means I can answer the question and then sometimes from there work out the molecular formula. So let's look at the question itself. So the question says, an alkene, really important there, alkene, so it's good for you to know what the general formula of an alkene is, and that's CnH2n. We'll talk about that later. It's completely vaporized, so basically turned into a gas, so we can use PV equals nRT. And then they give you a mass, 0.182 of the alkene, and they give you a volume of 167.47, a pressure, and a temperature. They want the molar mass and the molecular formula of the alkene, and you must show all of your working to get all of the marks, and we'll talk about those marks in a second as well. So the important thing is that you look at all of these and first of all determine the fact that you can use PV equals nRT. You've got, for example, any mixture of the components of PV equals nRT means that you can use it. So let's put this over to the side, okay, and then look at our 2 equations. So our 2 equations, PV equals nRT, and then mass over mR. Now if I look at the actual question itself, we've highlighted the bits that you need to use or you need to change. So we've got 0.182, and we've got 167.47 centimetres cubed. I've highlighted the centimetres cubed, and I've left the conversion down here. So you can see that we're going to need to convert centimetres cubed into metres cubed, okay, and we're going to need to convert kilopascals into pascals. Now, I haven't highlighted the K because it's already in Kelvin. We do need to use that number though, 313, which is the temperature, but we don't need to convert because it's already in Kelvin. So these are marking points that's really, really important, is that in so many mark schemes on PV equals nRT, the rearrangement of PV equals nRT gets you a mark. So even if you don't understand what you're doing, essentially, do that, okay? So if you rearrange it to equal number of moles, because you're given a pressure in the question, you're given a volume, and you're given a temperature, and R is a constant. So if we then start to work this out, we can start with our N up here. Okay, so our number of moles is going to equal our pressure. Our pressure is 101 kilopascals. Our conversion from kilopascals to pascals is times by 1,000. So it's 101, okay, and that is in pascals. We then times that, as we got in our rearranged equation, times that against V. Now V is 16747. Now here's the clever tip. So your tip is that when you do this, you are looking at your calculator, and if you want to turn 16747 centimetres cubed into metres cubed, just use the times 10 to the x button and put -6. If you put -6 in when you use the times 10 to the x button, it will automatically do it. Or you can just divide by 1,000,000 or divide by 1,000, then divide by 1,000 again, as we got here. But I'm going to do the calculator version, so I'm just going to put 167.47. Okay, and I'm going to times that by 10 to the -6. Right, and that is now in meters cubed. Okay, and then we do our division. Our division here is RT. So R is 8.314. Okay, and the units are joules per Kelvin per mole. I don't always put the units in when I do this, and that's because there's not always space, but there's space today, so I'm putting it in. Okay, so if I then look at the temperature is 313. And there's Kelvin. Okay, so we've put all of our numbers in. What I do recommend is if you're using a calculator, put this number in, then this number, and this is only if you're not used to using calculators. If you do maths all the time, you won't have a problem with this. But if you times these two numbers together, do that calculation first, and then divide by this and put brackets around it in your calculator, times that by that. It sometimes gets rid of obvious mistakes in terms of order of which you do these transformations. So if we do this, that is then going to equal 6.49 times 10 to the -3. Okay, and that is our number of moles. So we've worked out our number of moles. Remember, that is our N. That is our N, okay, when we've rearranged it. And then this is our N down here. But the important thing is, from the question, we have to work out the molar mass. The molar mass is the molecular mass, which is this MR down the bottom here. Okay, so we need to rearrange this equation to equal MR. And we know it's going to be MR, so we don't need the AR either. So let's just do that. All we've done is rearranged. Okay, so it equals MR. And that's what we're going to do now. So MR, which is our second section, okay, so MR, okay, is going to be equal to our mass. Our mass is up there, 0.182. Okay, and then that is divided by our number of moles. Our number of moles is up here, so from up here. So that is 6.49 times 10 to the -3 moles. Okay, and then in the end we get a number which equals 28. Okay, and that's 28 grams per mole. Okay, so we have 28 grams per mole. We have the molar mass, which is 28, but we don't have the molecular formula of the alkenes. So the clever thing here is now to think about alkenes. So if we think about alkenes, go from the simplest alkene you can think of. So the simplest alkene you can think of is ethene. Okay, so, and its general formula is CnH2n. So therefore, if I have ethene, this will be C2, 2n, H4. Okay, so C2H4. So we're going for, that is our simplest one. And then we can go up and go up and go up. But we can use that to check. So let's check and see what the molecular mass of the simplest alkene is. Okay, and that means there's 2 carbons, so 2 times 12, and 4 hydrogens, so 4 times 1. So 2 times 12 is 24, and 4 times 1 is 4, so 24 plus 4 equals 28. Okay, so the molecular mass of that is 28. So therefore, this here is going to equal C2H4. Okay, and my molar mass is 28, and my molecular formula is C2H4. And that is how you use PV equals nRT to determine a molar mass of an alkene. Our last question is probably one of the most complex questions you're going to do with PV equals nRT, and that is to determine the molar mass and molecular formula of a compound. And this compound this time is with chlorine or bromine, as you can see from the title. Chlorine reacts with oxygen, so we know we're making a compound, or a molecule, sorry, with chlorine and oxygen in it. We just need to determine how many chlorines and how many oxygens. We vaporise a certain mass of it, which is given in the question, and we've got a volume, we've got a pressure, and we've got a temperature. I would encourage you, if you're watching this video, to probably pause and then do this question at this point. Okay, but let's move that over to the right again. So we have PV equals nRT, as we did in the previous question, and we have our molecular mass equals mass divided by moles, as we used in the previous question as well. We've got all of our data highlighted again. We know it's chlorine and oxygen, so it's a chlorine and oxygen type compound or molecule. And it's vaporized with that mass. And we've got a conversion needs happening here, which is why we've highlighted centimeters cubed. We need to convert that to meters cubed. Remember, we can do that by dividing by 1,000,000 or using your times 10 to the x button. Okay, and then we don't have to convert our pressure because it's in pascals, but we do have to convert our temperature because it's in degrees C. So we'll go through this one a little bit quicker, okay, and straight away go to our N equals PV over RT. We've rearranged, okay, and we have an equation there to equal number of moles. We then put all our numbers in. So I'm putting my numbers in for pressure, 1 times 10 to the 5. I've got my number for the volume, but I've put my times 10 to the minus 6 in on the calculator, which turns it into meters cubed. We have got our gas constant times our temperature, and we converted our 60 degrees into Kelvin by adding 273 to 16. Your conversions again are in the corner. That turned out to be 5.99 times 10 to the minus 3 moles. And again, keep that number in your calculator. Use the ANS button, the ANS button. I use that all the time if I'm doing these. Okay, and then we know we've got N, we know we've got a mass. So let's put that into our equation. So we've got 0.405 divided by that number of moles. And we get a molecular mass or a molar mass of 67.5. Now the question is not finished here because you've determined the molar mass, but you have to now do the molecular formula. And this is where the little trick happens. So if we look here, we've got 67.5. We don't know what the substance is. That's why there's a question mark there. We've got 67.5. And let's just find out if we take away the mass of chlorine away. Now it's highly likely we've only got 1 chlorine. And the reason is because we don't have a whole number. And chlorine is 35.5 on the periodic table. Because chlorine is 35.5 on the periodic table, take that away from there and you end up with 32. So if you've got 32, you then need to think, well, does that fit with oxygen's mass? Now, oxygen has a mass of 16. 16 times 2 is 32. So this looks likely that it's going to be two oxygens because we have 32 and 1 chlorine. And in fact, the answer is ClO2. 1 chlorine, 2 oxygens. Simplest way to do that is if you have something containing chlorine, okay, look at the molar mass and take chlorine away. If you see a 0.5, it's more than likely 1 chlorine, okay, 1 chlorine. If you see chlorine and it's a whole number, it's more than likely to be 2 chlorines. Okay, this can also happen with bromine. Now, bromine has a molecular mass, a atomic mass of 79.9. Because it has 79.9, that means you'll see, if you had a compound like this, you would see a mass that had 0.9 on it. If it was 0.9, it would be 1 bromine. If it was 0.8, it will be 2 bromines. For example, if it was 0.7, it might be 3 bromines. But I very much doubt they go up to that level, and I think they're most of the time going to stick to 1 chlorine or 2 chlorines or 1 or 2 bromines. Anyway, that is how you do PV equals nRT with chlorine or bromine to determine the molar mass and the molecular formula of those type of compounds.